what do we conclude about our null hypothesis based on this probability? Failed to reject. So it appears to us that this amount of variation is fully consistent with random chance. We have no reason to believe that this is other than a 1-to-1-to-1-to-1 ratio. Now, it could be because this is a very small sample size, or it could be because this is 1-to-1-to-1-to-1 is the true ratio. We don't know at this point. But what we do know is that we cannot reject the null hypothesis. Does that make sense too? There's something very unsatisfying about the null hypothesis, you know? It's null. You're usually testing something that you don't want to be true, like the new drug I spent my life developing doesn't do anything, you know? You're asking a question you actually don't want to be true. But what's powerful about this is it allows you to evaluate the strength of your data. Is your data strong enough to reject the null hypothesis, or is it not strong enough? Any more questions about? Yeah.
So isn't it if it's greater than 0.95, then we fail to reject? I thought it had to be like over 95%.
Okay, so this is. Let me just. So this is the p-value. Let me just write down some of these p-values. So there is a 0.97, 0.75, 0.25, 0.25, and then it goes on. So these are the p-values, and they represent the certainty that your data, they represent the certainty that your variation is due to random chance. So we typically take 0.05 as the cutoff where we reject HO. Because at this confidence level, we have a 95% certainty that our data is telling us there's a legitimate difference between the expected and the observed. Does that make sense?
Yeah, I just had a flip. So like 25 versus 0.95.
Yeah, versus that. So this is our certainty that if we repeated the experiment again, we are about 95% certain that we would get data that vary this much or more simply by random chance. Assuming 1-to-1-to-1-to-1 is the true value. So this is a way of sort of deciding how much error we are willing to live with in a test.
Would you mind explaining number 7 on the overview? The one with the dihybrid cross?
Okay. Okay, so this traits involved in a dihybrid cross are unlinked and do not interact genetically with each other. One trait is represented by codominant alleles, but the other has dominant and recessive alleles. What phenotypic ratio will be observed in the F2 offspring? Okay, so first off, how many in the codominant, how many phenotypes are you going to see in the F2? 3. So, for example, if we have codominant AA and BB, we'll get the P, AA, BB, the F1, AB, and then the F2 will be AA, AB, and BB. So we will have 3 codominant phenotypes. And at what ratio will these phenotypes appear? 1, 2 to 1. Okay, because this is just, you know, you can do a Punnett square and figure this out. There's one way you can get AA, there's one way you can get AB, but there's 2 ways you can get AB. Did I say one way you can get AA, one way you can get BB, but 2 ways you can get AB. You can get A from your mother, B from your father, or you can get B from your mother and A from your father. You know, this is just a Punnett square. Okay, the other has dominant and recessive alleles. So, what will the phenotypes of the other trait, how many phenotypes will the other trait produce? 2. And what will the ratio of those phenotypes be? 3 to 1. So, you can do this by doing a fork line method. 1/4, 2/4, 1/4, and then 3/4, 1/4, 3/4, 1/4, 3/4. Okay, so this represents all possible combinations of the codominant alleles and the dominant and recessive. So this comes out to 3/16, 1/16, 6/16, 2/16, 3/16, 1/16. So we get a 1-to-1. You get 1, 1, 2, 3, 3, 6. Okay. Do any of these answers have 1, 1, 2, 3, 3, and 6? Yeah. So I think this is probably about the fastest and most reliable way of calculating this kind of ratio. And if you have done this correctly, it should add up to 16/16. So we have 4, 10, 12, 15, 16. So it adds up to 16/16. the point of learning how to do this method, it simply represents random assortment of all the traits. And it gives us the expected proportion that we will get for each one of the phenotypes. And note that you can do this a heck of a lot faster than you could generate a Punnett square to do this kind of calculation.
Is that also how you do 8 through 9 instead of making it track on its bill?
Mm-hmm, absolutely. So let's do 8. A true breeding tall leaf pea plant with smooth green seeds. So, GG made it to BBWW. Okay, in the F2 generation, what proportion of the offspring will have the dwarf smooth green phenotype? So take these characters one by one. What proportion of the offspring will be dwarf in F2? Okay, so BB is 1/4. How many will be smooth? 3/4. And how many will be green? 1/4. Okay. So you multiply these and you get 3/64. Okay, in the F2 generation, what proportion of the offspring will have big D, little w, big G, genotype?
164.
Okay. Tell me how you got that.
Because having big D, that's 1/4,
Mm-hmm.
and little w, same thing. Big G, same thing.
Mm-hmm. Excellent. So this